can now enjoy fully the last talk of this wonderful conference with the great Jim Weatherall, telling us about something.
Yeah, thank you. So this talk is this talk is going to be an experience of mutual discovery, self-discovery for me, as we all learn what it's about. I gave Chris a menu of options for talks. There were 4 talks, and he gave me absolutely no feedback on which one to select. He'd send me some reminders that I had to choose between them, but he gave me no guidance. And I ended up choosing this one, which I now deeply regret. I didn't give him this title. I did give him a different title. This is the title that I gave him. And the reason I ended up going with this talk was that the last time I gave the other talk I was leaning towards, it took 2 full hours, and we did not get through all the material. And I thought, Shelley was there for it. I don't think that I can cut that down. So what I'm going to do is I've got 1 slide at the end on that material that I've just sort of appended to this other talk. And this talk seemed topically appropriate because it's very much indebted to themes from Howard Stein, much less George Smith and Bill Dimopoulos, unfortunately, but maybe this will balance out some of the other talks. Okay. This is a picture of the Big Dig, which Chris and I were talking about last night. I guess, actually, I was talking about with Chris and Lydia and Mike, which, I think of as a kind of a metaphor for what I'm doing here. This is very much a project under construction. It is a long project. It is far over budget. And there's a serious concern. I don't know if anyone knows this, but the Big Dig went for 25 years. The year that they finally finished it, part of it collapsed and actually killed someone. And so this is the sort of thing that, is, okay. It's very programmatic. If I had chosen one of the other talks, you would have gotten something that looked more like an original philosophical argument or a contribution to, foundational work in physics. This isn't quite that. It's more of a reflection on sort of big picture views in the philosophy of physics, connecting important themes, motivating a lot of my work, but I think also providing a perspective on core issues in the foundations of physics that I think, well, what I want to argue is that many people in the field are thinking about these things in ways that I would like to reorient. And I'd like to do so along Steinian lines. So both TBD and the other title, Structure, Laws, and Symmetry, are kind of descriptive. Structure, Law, and Symmetry is literally just an outline of the talk. They're just going to have 3 sections. We'll get to the outline in a bit. It has 3 sections. One's called Structure, one's called Laws, and one's called Symmetries. Let me, though, give you a little bit of a motivation. I mean, I'm going to be touching on lots and lots of themes, but let me begin by observing something about the recent literature in philosophy of physics. So since around 2002, there's been a large and active field in philosophy of physics that many people in this room have contributed to, actually, on how to understand symmetries in physics. Okay. I should put the text up before I say it, so let me move forward. Among the questions asked are things like, what are symmetries? Are they properties of theories, or are they guides to or motivations for theory construction? So you get motivationalists about symmetries. You get, you have family of views here. Do they have empirical consequences, right? And so there's a large literature on whether they're direct or indirect empirical consequences of symmetries. Is there some sense in which you could read symmetries off of phenomena in nature? Or are they just properties of theories that have a different kind of character? There's a literature on whether they're stipulated or discovered. And so stipulationists about symmetries have the view that we just say what the symmetries of nature are, and that's somehow part of specifying theoretical content. And other people feel that it's somehow in the process of analyzing our theories that we discover that something was a symmetry of the theory or maybe a symmetry of nature. One thing I think we see a lot is an instinct that many philosophers of physics have, following some physicists, that it's bad for a theory to have symmetries. That if you find a theory that has symmetries, what you should do is try to reduce it. We should try to get rid of the symmetries. We should find a different theory, or maybe reformulate the theory, or maybe reinterpret the theory, maybe learn to become sophisticated about the theory, but somehow eliminating the symmetries. And then finally, there's this general question. We have theories with symmetries. We can't figure out how to get rid of them. How are we supposed to, make our way in life? So what I want to do is say this pretty large literature is leading with the wrong thing. It's taking symmetry as the object of analysis, whereas I want to say that is a tool of analysis. It's a method for analyzing structure, specifically structural relationships between different parts of our theories. And so what I want to advance is a structure-first account of symmetry, where I want to reorient questions to first, what are we claiming about either the structure that our theories attribute to the world, or the ways in which our theories use structure, invoke structure, have unnecessary structure, have auxiliary structure, questions like that symmetries end up allowing us to investigate. And so basically, when we use symmetries, what we're doing is understanding through symmetry-based reasoning questions about representational adequacy, relations between structures in our theories. All right. The language of structure first here. So, this talk, I first gave it at the second of two conferences that we had in Irvine with David Wallace and some of the people in San Diego, and then we brought various people in around math for structural realism, the view that David advanced a few years ago in a paper called Stating Structural Realism. And so this structure first is supposed to be, in some sense, a nod towards math first structural realism. Okay, so I want to defend a few big claims about symmetry, but this is really part of a package of views that I'm going to try to present to you. I'm not going to be able to defend everything. I will do my best to be clear about how the pieces are supposed to fit together. The big picture claims about symmetry specifically are that we should not expect a univocal account of symmetries in physics. There's not going to be an answer to the question, what is a symmetry in physics? Symmetry-based reasoning is context-specific. We use it all sorts of ways in physics. Similarly, we're not going to have an account of the symmetries of a theory that's going to be satisfactory in all situations. In fact, I'm going to argue that we don't really have an account of symmetries of a theory that does any of the things that is sometimes said to be done by such a thing. And instead, what I'm going to say is that there are many, many examples of compelling symmetry-based reasoning, all of which I want to argue are ultimately illuminated by shifting focus to the structures that are being transformed or not transformed under some class of maps that we're calling the symmetries. Okay, so what I'm going to talk about is, I think indebted to many, many people. There's only so much space on these slides. There are many other pictures that I could have put on. These are some pictures that I found kind of entertaining, and so I chose them. So this is Howard and Abner Shimoni speaking to one another. I think what I'm going to say, in my view, what I'm going to say is heavily indebted to Howard. I met him several times, 3 times, I think, in total, corresponded with him. But I also did a course on him where we read all of his work sort of as a body. I had a student who wrote a dissertation on Howard, or with a substantial chapter on Howard. And I feel like there are unrecognized connections between different of his papers. One way of getting at what I have in mind, though, when I'm talking about a structure-first account of symmetry or a structure-first approach to symmetry, is to say, look, in my view, one of the most important instances in 20th century philosophy of an analysis of symmetries in physics is in the paper Newtonian Spacetime, Howard's first publication, right? And in modern presentations, I mean, so for instance, in World Enough in Spacetime, when John Ehrman talks about this, the presentation is we have these different spacetimes with different symmetry groups. There's the Galilean group and the Newtonian group, the Leibnizian group, the Machian group, and so on. And it turns out that the dynamics are invariant under one symmetry group, whereas Newton thought spacetime was invariant under a different symmetry group. And that's a failure of symmetry matching. And so really what we want to do is move to a different spacetime structure so that our dynamical symmetries and our spacetime symmetries match. And then, of course, we have a more modern literature with Simon as the main instigator, but also Eleanor Knox and David Wallace and many others following Simon, arguing that no, there's an even larger symmetry group that we should think of as the dynamical symmetry group in Newtonian physics properly conceived, and that would lead us to yet a weaker spacetime structure. Now, here's the point that I want to make. Howard gives this argument in his original paper without using the word symmetry. That's not part of the argument. What he does is he gives us 2 presentations of what he's going to call neo-Newtonian spacetime structure, and he shows why this is the structure that you need in order to make sense of Newtonian gravitation, in a fairly precise sense of make sense of. Symmetries are implicit there. But the mystery is, how do I compare the structure of spacetime to the structure presupposed by the equations? And then later on, we see we can illuminate that question by reasoning using symmetries. It's not that we discover this fact about symmetries and then that is somehow the starting point for analysis. Okay. Do I need to name everyone? Do people know who these people are?
That's a good idea. I've met all those people.
You've met all of them?
Younger people who might not recognize them.
All right. Well, this right here is Thomas Barrett, who doesn't always have that mustache, but looks, I think, pretty great with it. So, David Wallace. This is Penn Matty. This is John Ehrman. This is David Malamant. This is Hans Halverson. That's Carrie McKenzie, another former local. Jill North and Mark Wilson. Okay. Good. So here's the overview. As I said, it's just the title of the talk. I want to begin the first section here by talking about another paper of Howard. So this is just what it says it is. It's on spacetime and ontology, that description of the content. It is an extract of a letter to Adolf Grunbaum. It runs to something like 30 typeset pages, which makes me wonder how much was extracted, like how much was left on the cutting room floor. And it's wonderful. I mean, I don't know if people have read this. It's in the 1977 Philosophy of Space-Time volume from the Minnesota Studies series that combined 2 conference proceedings. It was a conference that was held in Minnesota and a conference that was held in Boston. The second one was like a kind of Grunbaum fest, and the first one was just a philosophy of space-time thing. Many funny stories about that Minnesota conference. John Ehrman was in Minnesota at that point. I will in the Q&A, if there's not enough questions, I'll start telling funny stories. I do have to stick to, I'll tell you Bildamopolis and the Snake, which I now know the ending of. Okay. What's fascinating about this paper is that it anticipates a great deal of the last 20 years of literature in philosophy of general relativity, particular on the question of what gives the space-time metric geochronometric significance. And so Grunbaum and Stein are arguing about this in a way that looks very, it's not, the positions don't exactly line up. It looks very interestingly similar to much more recent debates between dynamical relativists and people who adopt various versions of what's sometimes called the geometric view. But I want to highlight a particular passage, which is, I think, connected to some of the things that Mike said and that was in our exchange. Howard says to Grunbaum, you tend to think of the world in terms of things, primary substances in Aristotle's sense. I do not. I tend rather to think platonically of structures and aspects of structure. Then in parentheses, forms, question marks. I'm not going to talk about forms anymore. I'm going to talk about structures and aspects of structure. So what do we mean here when we're talking about structure? So Howard never tries to give us an account of structure. What he does, even in Newtonian space-time, is present the idea that the world is structured in certain ways or carries certain structure, has certain structure, has the structure of neo-Newtonian space-time, or in later work, has the structure of Minkowski space-time or relativistic space-time. And the idea seems to be something like, there is in the world whatever is needed to make certain kinds of claims true, like certain kinds of claims about relative velocity or about acceleration, but not certain claims about absolute velocity. And so it's something about what we can really express about the world or what sorts of claims could be true of the world. Now, what I just said was rough. What he says is also rough. Maybe what I just said isn't the perfect way of encapsulating what he says. The important thing, though, is that he certainly does not attempt to do something that looks more like a formal account of structures, giving us an account of what a structure is, such that that is the kind of thing that we should be thinking about. And so what I want to suggest is that this is a good thing, actually. Maybe one can be more explicit than he is, I'm not sure, but the way that he says he tends to think, right, is this tendency, not exactly a position, but the way he says he tends to think is one that is structuralist in character, but he avoids what I see as a kind of philosophical error, which is quite common in much of the literature in either structural realism or structuralism more generally, which is to try to give a general definition of what a structure is. So we see this all over the place. We see this in math. We see this in philosophy of math. We see this in 1970s structuralism, 1960s structuralism. We see it in accounts of the semantic view of theories. We see it more recently in work on structural realism, where you begin by trying to give a mathematical theory of structure where you start with something like standard logic or standard model theory, and then you modify it in such a way that instead of talking about whatever it is that logic was supposed to be about or mathematics was supposed to be about, you're now talking about just structures. Now, one of the things that I take away from David Wallace's Math for Structural Realism is this idea that that's the wrong way to go. Like whatever we should be doing when we're trying to present some form of structuralism or talk about structure in this kind of way, it shouldn't be to first give an account of structures. The reason is we already have a rich and successful way of theorizing about structure, and it's just mathematics. Group theory is our theory of group structure. Differential geometry is our theory of manifold structure. In some sense, when we say that the world has a certain structure, what we're saying is something about the way that our normal applied mathematical methods that we've sort of developed via a process of cultural evolution over the last 500 years or so allow us to successfly reason about the world using this particular kind of mathematics. We say and this is what I mean when I say, or I understand Howard to mean when he says that, Newton is, Newton is saying something about the structure of the world. He's saying something about the world having Newtonian spacetime structure, whereas in fact, probably he should be saying it has neo-Newtonian spacetime structures. It's the kind of reasoning that we use in the context of what we now call affine geometry with a certain kind of metrical structure that would is like sort of reliable for reasoning about the structure of space and time for certain kinds of purposes. And we don't need any other definition of structure. It's just the application of the math itself. Now, I recently reread David's paper, and I don't know why this was a takeaway from the paper, actually. I don't think he says this in the paper. I originally read an early draft of it and read the draft and immediately saw him give a talk on it and had a long conversation with him about it. And then, so, I'm not saying that this is going to be anyone else's takeaway from that paper. I think that he does, what he does do is reject the idea that we need an account of structure. I think that he does say that when what he is trying to do in stating structural realism is give us a way of thinking about structural realism that doesn't involve some sort of modification of model theory or something like that that's going to tell us what the structures are, and then there's going to be some other step of saying, here's how the structures relate to things in the world. Okay. I remember changing the title of the slide to this, and I now have absolutely no idea why I did that, because it's a slide about logic. Let me just put the content. I wish I could just delete. I'm just going to put the content up. One of the places that I disagree with David in his in that paper, which is going to sort of introduce another theme that's going to be relevant in a little bit. He's very concerned about uses of what he calls predicate persistification or language-first approaches. And he sort of identifies language-first approaches to analysis of theories with analyses that run through logic. I think that there are different attitudes you can take towards logic, and what I want to advance is the idea that the right way of understanding mathematical logic is itself as an instance of applied mathematics. Applied mathematics of what? Well, applied mathematics of mathematical reasoning. So the idea is basically, look, we've learned how to do math, we've learned how to do applied math, we've learned how to do pure math, we're pretty good at doing it. One of the things that we'd like to apply math to is to math itself, to better understand or be precise about the kinds of relationships that we have in mind when we talk about the relationship between some mathematical theory and some structure in the world. How do we do that? Well, we introduce a new mathematical theory. On one side, the mathematical theory is a mathematical theory of syntax. And then in addition, we introduce a mathematical theory of semantics. Now, you can actually see this historically, right? So Gensen presents himself, in his work in logic as attempting, or in natural deduction in particular, as attempting to give a mathematical theory of mathematical reasoning. He says that explicitly. It's less clear that that's what Tarski has in mind, right? Tarski, I think in the first instance, is trying to show that the logical positivists are wrong about truth, that you can be perfectly clear about truth. But I think the one way of understanding what's going on there is that we're giving a mathematical theory of how precisely formulated mathematical claims could be true about something. Of course, the way we do that is by building models within set theory and then giving a formal process of interpreting them. Now, I think that set theory should be interpreted in the same way. It's sort of a background theory of set structure that turns out to be quite useful in developing this kind of model theory, among other things. Okay, now, I think a couple of things are true, and this is connected to that previous slide. I want to say that none of these viewed as mathematical theories should be understood as, I guess this is why I have this title, none of them involve or imply ontological claims. And so this is part of the reason why I don't think that the right way of being a structuralist is to start by giving an account of structure. One reason is we've got perfectly good accounts of structure. The second reason is these perfectly good accounts of structure aren't, in some sense, anti-structuralist the way many structuralists seem to think that they are, because sets somehow involve individuals, and there's some sort of implicit notion of reference to things involved in doing set theory. I think that we should think of set theory in a perfectly structuralist way, and we should think of mathematical logic in a perfectly structuralist way. And that, in fact, is kind of anti-structuralist to give an account of structure. Okay. So you might think that what I'm gearing up to do is advance a form of structural realism, which is not what I'm going to do. David did that. I'm not doing that. Right? I'm doing something else. I am trying to push this idea that one should tend to think in terms of structures and aspects of structure a bit further. So here are two common versions of structural realism that one encounters in the wild. There's epistemic structural realism. It's the structural aspects of our theory that are most likely to persist in future theorizing. Of course, there's a sense in which that's true if we understand the words in the right way. I think there's a lot of nuance. I'm not going to say too much more about that. Ontic structural realism, the fundamental ontology of the world consists of structures. This is the kind of thing that I'm just rejecting, actually, because I think that it's predicated on giving some prior analysis of what a structure is as an ontological category that I think is not the right way of going. If anything, I want to advance a kind of structuralist quietism, which is that applications of math and science involve attributing certain structure to the world. Those applications are consistently successful. That those applications are consistently successful is itself evidence that the world truly has the posited structure, at least approximately. And that's really all that it means to attribute this structure to the world. Okay, so there's another way of thinking about these issues that looks kind of similar to what I'm saying. With apologies to Carrie, I mean, this is just from a recording of a talk, and I took a screenshot that had the right slide, and unfortunately, it's an action shot of her. What she says is, she's sort of drawing on this von Frossen idea that empiricism is a stance, and that realism is a stance. And she advances the idea that maybe structuralism should also be thought of as a stance. And what she ends up with is, she gives some examples, right? So she says, okay, physicalism is a stance where it's a commitment to defer to physics with respect to what there is. Then structuralism is a stance. She says quite a lot more, but in the first pass, she says that the language of physics is mathematics. I don't totally agree with that either. In fact, I think that it's just too weak. What I want to say is that mathematical science works by supposing that aspects of the world have the structure that form the subject matter of the mathematics used. I've tried to say some things that are suggestive of what that means. I won't say them again. The key thing that I want to emphasize is that applied mathematics consists of methods for isolating those structural features of the world, manipulating the mathematics to inform our understanding of the target. Okay. There's a lot going on in this slide. It's got a bunch of pictures and some dynamical elements. Let me first tell you who everyone is. Okay, so this is Jill North. This is Tushar Menon. This is Mauricio Suarez. This is Katie Robertson. That's Neil Dewar, a young Neil Dewar who we're going to reject. And then Trevor Title. There will be an older, more mature Neil Dewar coming up in future slides. Here, let me just go ahead and, okay. Okay, so let me once again put the content up here. Okay, here's another way of trying to say what's going on when I'm talking about applied mathematics as attributing structure to the world. There's been a literature recently on perspicuity and what it means for some representations to be perspicuous and others not to be perspicuous. And so what I want to argue, and this is partly work that's in collaboration with Katie, is that the sense in which mathematical structures are well suited for representing or are perspicuous is precisely because of the way in which our inferential systems work. Our inferential systems, like the way that we reason in applied math about the world, is generally sound. And when it is sound, it's because the kind of reasoning we're doing in math is tracking truth about the world. This is, I think, a version of a view that gets called inferentialism. I want to be very careful about this, though, because Bob Random has written very, very long books about inferentialism, and I haven't read them. What I know is that Tushar and Mauricio have talked about versions of inferentialism. Tushar, in particular, has connected something like the idea that I'm talking about to Brandom, and I'm not sure that I'm not sure if he's right, but I take it that he has read Brandom. I mean, he said these things in Pittsburgh, and I think that if he hadn't read Brandom, he would have gotten in more trouble. Okay, so but what I'm trying to advance is a pretty rough idea. There's a lot to work out in the details, and I'm not sure exactly how it's going to go. But the picture is one where part of what gives our words meaning, or our sentences meaning, or our practices meaning, is the success of the reasoning that happens. So like the way in which we can draw inferences from certain kinds of assertions. And in particular, in the context of applied math, we have these rich structures of inference where, I shouldn't say the word structure there, but these rich patterns of inference and rules for inferring things that allow us to draw inferences about the world in a way that tracks how we draw inferences about the mathematical structures. And the kind of semantics that I want to offer, the way in which I want to say these mathematical structures are corresponding to worldly structures, is that it's the way that we can draw these inferences about mathematical structures that track reliable truth relations about things in the world. Right? And so, I can posit that something is, that some function describes the orbit of a planet, and then I can take its derivative, and I can infer that says something about the instantaneous velocity of the planet. Okay. Good. Why have I X'd out poor Neil and Trevor? Lovely people. Neil, because he gave a talk that I didn't like where he was arguing against perspicuity. I'm not going to go into that in any more detail. Trevor, though, Trevor has written this paper where he argues, it's called What Theoretical Equivalence Could Not Be, where among other things he argues, and Craig argues this too. Where's Javier? Yeah, Craig argues this too. Anything can represent anything. Right? And so Craig uses the example of a salt shaker, and he says this salt shaker could represent anything at all. I think he says it could represent Madagascar. And Trevor, has this idea of like radical semantic indeterminism, where literally anything can stand, and what he has in mind is a kind of denotation relation. I can just stipulate that this denotes that. And the point that I want to make is simply that is not how any of our successful representational practices in mathematical physics work. Right? Consider, for instance, whether or not you can tell anything about how sea level rise will affect Madagascar by putting your salt shaker into a pool of water. I contend you cannot infer anything reliable about that. And the reason is that although maybe there's some weak sense of representation, it's not the kind of representation that allows us to employ these inferential patterns that are so crucial to successful representation in mathematical science. Okay, and so there's a little bit of dancing around the key idea here, but I think that this is going to be the closest we're going to get to it. And then the final piece, and this is also indebted to David, is that the way in which we've come to have these inferential systems, the way in which we've come to have this conception of structure that we theorize about in mathematics that we apply to the world using sort of standard methods in applied mathematics, is via a long process of cultural evolution and development of cognitive capacities. And so this is just how we operate in the world, right? It's kind of a refinement of just how we've operated in the world forever and how, everyone operates in the world. Right? And so we have these evolved cognitive capacities for certain kind of mathematical, also spatial and arithmetic specifically, reasoning and representation. We learn to use those capacities sophisticated ways through practice and education. We refine previous iterations of the practice from earlier scientists. And ultimately, it's inherited culture, right? The reason this is the right way of doing it is because it has been successful for a very long time and people have gotten better and better at it. How many hours do I have? Okay, good. So I'm on to section 2 on laws of nature. Okay, so what are we trying to do here? I'm going to get to symmetry in a bit. From a moon's eye view, what we're trying to do in our scientific activity is identify some things in the world that we can figure out how to observe or measure or draw inferences about. I'm just going to use the word determinable. I don't have anything writing on that. If you don't like that word, use your favorite word. I'm not going to use the word observable, though, because that has a technical meaning that I'm not trying to invoke. Okay, so we come up with these quantities, and then we try to find relationships between them. The kinds of relationships that allow robust inferences of the sort that we've seen lots of examples of in some of the more historical talks, like or contemporary talks too, like Mikhail's talk and Lydia's talk I have in mind. We're going to try to characterize states of the world by specifying some of these determinables at a time, and then we're going to try to come up with rules that describe how those determinables are going to evolve over time, right? And so constrain future or past values of determinables given their measured values at a time. Okay, very abstract picture of what physics is about. Coming in a little bit closer, we can develop a measurement theory of these determinables, right? We find as some fact about the world that there are possible values, that the possible values of these determinables have some structure, right? They come in different values. They might be discrete. Maybe there's a semi-group. Maybe there's an affine structure associated with them, right? And so this is, sort of the beginning of a application of math to some of the things that we find that we can observe or measure. Now, eventually, what we're trying to do as we build physical theories is, identify those structures and then find fruitful relationships with them. Usually, this is in the form of equations. The most useful relationships are those equations that relate quantities from which many determinables can be determined. Right, so ideally, what we'd like to do is find something like, a quantum state, which allows us to infer expectation values for many different observables that we could go out and measure. Now, these equations that we try to find, that's what I mean by law. I'm not trying to give you a metaphysical account of laws. I'm just saying, as an observation about scientific practice, we very often do like to find these equations that have this very general character. I want to say that these laws generally are structural relationships between the kinds of things that I'm calling determinables. Not necessarily just equations relating observables, right? Equations relating things from which I can draw inferences about a lot of stuff. Okay, here's the big question. This is Howard's big question. Howard says this is Newton's big question. From my point of view, this is just the question that motivates me from the point of view of philosophy of physics. This is what I'm most interested in. We've got these equations. What structure must the world have, in the kind of sense that I've been talking about, for some given laws to be coherent and meaningful? All right, and so you can give this analysis. Howard, not in these words, but gives effectively this analysis for something like F equals ma. in Newtonian spacetime, right? And so this relates force to mass and acceleration. In order for this to make sense, force has to be a thing, mass has to be a thing, and acceleration has to be a thing. And it also better be the case that I have some way of independently understanding the two sides of these equations. This equation, I should have some understanding of what mass is, what acceleration is. And in particular, in the Newtonian spacetime case, the thing that's really important is to say what I need to say about space and time in order for acceleration to make any sense. I mean, of course, what I have to say about bodies for mass to make sense is also an important question, and one that was discussed, for instance, by Miguel. I mean, it's like a serious problem for hundreds of years. Likewise, one of my favorite equations, Einstein's equation, similar kind of thing. You can say, well, we're relating the stress energy of matter to some facts about space-time geometry. What has to be true about the world for this equation to make any sense? Among other things, it has to be the case that there are some facts about length and distance that we can encode in this kind of metric. And moreover, I need to be able to think about the differentiability of that structure such that I can come up with a notion of the curvature of space and time. Matter has to be represented in such a way or structured in such a way that I can make sense of its energy and momentum properties. You can ask, what's the minimum amount of structure that I need to make sense of this, right? And so lots of debates in the history of general relativity have come down to under what circumstances have I secretly presupposed something in addition to the minimal structure needed to make sense of an equation like this? Okay, all right, I'm actually going to stop on this topic and here's the more modern, mature Neil, my collaborator. You can ask further questions like, what account of laws is needed here? We say it's not Humeanism. We have a paper on that. Chris and I, allegedly, as soon as we finish our book on cosmology, are going to write a paper on this kind of epistemology of laws, or the epistemology of laws in this sense. Okay, so let me now finish the talk. Okay, so what are symmetries? Symmetries, so I think of symmetry as a weasel word, right? So it refers to lots of different things in physics and in philosophy of physics. Sometimes we talk about automorphisms of a mathematical structure. Sometimes we just talk about isomorphisms. Sometimes we mean something more vague, maybe something pre-theoretic. Sometimes we have in mind transformations between mathematical representations of the world that are not isomorphisms, but which we think represent indistinguishable states of affairs. For me, today, I'm just going to stipulate that symmetry means automorphism, just to be clear about what's going on in the rest. So an automorphism is an invertible structure preserving map from some structure to itself. I'm not, doing this is not the thing that's going to resolve all of the issues about symmetry that I raised earlier, right? This is just to be clear in my own presentation. Okay, but what this means is that before we can say what symmetries are in any given context, we first need to say what structure we're talking about and also say what it means to preserve that structure by some sort of transformation. And so this account of symmetry, this way of thinking about symmetries is quite far downstream of doing a lot of theorizing about the world, right? We're not introducing symmetry as in some pre-theoretic context as a description of between states of the world as an automorphism of some structure. Okay, so why do I think you should care about symmetry? The idea here is that it's just as a standard part of mathematical practice. This is something that all mathematicians are doing all the time. They're looking for structure-preserving maps associated with the structures that they're interested in. The reason is that this is how you specify the target of your mathematical theorizing. Right? This has nothing to do with physics right now. We're just, I'm building some stuff and then I'm trying to tell you what part of what I've just built is the thing that I'm actually interested in, right? What is a group? Well, I can give you some axioms, or I can say, well, a group is a set of elements and some operations, and any map from those elements to themselves that preserves all the operations is a group isomorphism. That preserves all of the group structure. It's the thing that's preserved by that map that I mean by group. Okay. Okay, and so you can make this all precise in the context of model theory, and you can make precise the idea that automorphisms of a model have something to do with what's expressible about that model, and this sort of goes back to this theme that I introduced but didn't really say enough about attributing structure to the world as saying something about what it makes sense to say about the world. But that's going to be just sort of a dangler. Very often, the way that we build things in mathematics is to construct them in set theory and then pair by specifying what the symmetries are. I mean, this is like standard in the sense that like you open a math textbook and it's like, what is a manifold? Well, it's a set, and you've got some charts, and then you've got diffeomorphisms, and it's the thing that's preserved by the diffeomorphisms. Okay, so what do we do in practice? Mathematicians, but also physicists and philosophers of physics are often impressed with arguments that invoke symmetry in some way. So here are some examples, right? The whole argument, the gauge argument, Leibnizian shift argument, surplus structure argument. As I said at the very beginning, one strategy that people sometimes adopt is to try to say, well, what is the thing that all of these have in common as instances of successful uses of symmetry? Maybe we can identify some underlying inferential pattern or symmetry concept that makes all of these compelling. And it seems to me like what actually they all share is that they use a class of maps that either do or they think should preserve some structure and make arguments about dependence of different structures based on that. One way of seeing how this reasoning often goes is to think about Beth's theorem in first-order logic, where something is explicitly definable in some theory, just in case it is invariant under all of the symmetries of the models of that theory, right? And so the idea is that like what does and doesn't change under some class of maps that preserve one thing is going to tell you what I can build out of the thing that's preserved. And that, of course, is going to tell you what does and doesn't depend on certain kinds of structure. Okay. Now, what can't symmetries be? They're not going to be things that fully characterize structure. And there are all sorts of examples that we can give where symmetry is just trivialized. They aren't the right way of describing structure. They're not good enough. But there are cases where they're very useful. They can't be prior to some kind of partial or preliminary physical theorizing. You have to have some idea of what sort of structure you're preserving or not preserving to ever apply symmetry reasoning. They're not going to determine what's measurable, observable, or real. What's going to determine what's measurable, observable, or real is like what we're able to measure, observe, or what is true of like real in the world, right? Like that's the thing about the world, not a thing about symmetries. They can't just be arbitrarily stipulated in addition to other kinds of structural claims about the world. Okay, now, in 2001, the great philosopher Gordon Bellot introduced this crucial principle of sufficient reason that some of you may have heard of. It was in the Journal of Philosophy. Okay, so do people know this paper? It's a classic. It's not really about the principle of sufficient reason. I would say that it's really about symplectic reduction in Hamiltonian theories. But he's one of the people who sort of advances this idea that we encounter theories in physics which have symmetries and which therefore have a problem. And the problem is that somehow they're odious. The symmetries signal that, the symmetries of the theory ipso facto signal that there's a redundancy in the theory's ability to represent situations. And he uses methods of symplectic reduction to take a Hamiltonian theory and construct a new Hamiltonian theory, which is a reduced version. Okay. I think he's inspired by Carlo, actually. Yeah, the early 90s and late 80s. Yeah, it's these Pittsburgh. Okay. You probably talked to Brandom too, didn't you? These long books back in Pittsburgh. Okay. So the picture I want to lead with is that in order to speak about the symmetries of a theory, right? So if that's an idea that we want to pursue, the idea that is the symmetries of a theory that are going to guide something about physics, we first need, on the way I've set things up, we first need to say what a theory is as a mathematical structure. we need to actually like mathematize the theory itself. In order for this to be compelling, it had better be the case that our mathematical theory of physical theories characterizes all the structure that we really want to associate with a theory. Otherwise, it's not really clear what we're doing when we talk about symmetries of the theory. Now, Gordon himself is actually totally fine on this point, right? Because when you're talking about variational symmetries or Hamiltonian symmetries, other people talk about auto-translations. Let's just keep with variation and Hamiltonian theories, Hamiltonian symmetries. I mean, you have a pretty good theory of a dynamical system of the sort that you're interested in. You do understand what the transformations are. These are symplectomorphisms that preserve your Hamiltonian. They really are preserving the whole thing. So we can do this sometimes. The issue is that very often this idea that we're going to take a theory, identify its symmetries, is misapplied in cases where we haven't given a mathematical theory of theories such that we can talk about automorphisms of the theory. Instead, what you have in mind is a class of maps that are like usually helpful for probing structural dependencies in the given theory. So here's an example. Diffeomorphisms in general relativity are often described as the symmetries of general relativity. They're very, very useful for probing structural dependencies in general relativity. I want to maintain that there is no useful sense, actually, in which we should say the diffeomorphisms are the symmetries of general relativity, at least in the sense of that there's a mathematical structure, general relativity, which is, a mathematical representation of the theory, and these are the automorphisms of that structure. They're doing a different kind of thing. Okay, I'm not going to do that. I can make this idea precise. Here is what a generally covariant field theory in n dimensions is. It's a functor from the category of n manifolds to fiber bundles, and a subobject of the kth jet bundle of that functor for some k. Perfectly, this is like a very, I can say what's going on here in questions. I don't have any time left, unfortunately. But this is like a nice compact way of capturing like basically all of your intuitions about what a generally covariant system of partial differential equations should be like a diffeomorphism invariant system of partial differential equations. It's a nice mathematical thing, right? It's basically two functors and a natural transformation between them. A symmetry is going to be a natural transformation from F to itself that preserves the subobject. So totally standard looking example of mathematical structure and automorphism. Now, it turns out that there are no field theories that have symmetries, or at least I don't have a proof of that, but like none of the examples of field theories that you're used to, none of the examples of symmetries of theories that you're used to work out as symmetries of those theories, right? So gauge transformations are not symmetries of electromagnetism. Diffeomorphisms are not symmetries of general relativity, and so on. Yes, I understand. I'm done. I'm almost done. Okay. The thing I want to emphasize, though, is that the only way we get to this analysis is by invoking a ton of symmetry-based reasoning, right? The fact that we're talking about functors in the first place should already be a signal that everything you're interested in here is what transforms properly under what classes of transformations and how to map those between different contexts. All right. I'm just going to skip the whole argument and finish. Yeah.
Scanning. Okay, we start there. Just yeah.
So your talk emphasizes the primacy of mathematics as structures. How worried should we be about Gödel's undecidability theorem? Not worried at all?
Not worried, no. Yeah.
Like, for example, the continuum hypothesis is an undecidable proposition, and the continuum hypothesis is about the cardinality of like space-time, presumably. At least that's how we treat it. Of course, it may not mean anything that that you don't have to have the continuum hypothesis. Anyway, I'll let you.
Yeah. I'm not worried about this.
Nothing in physics depends on that.
Yeah. But I think so Wayne is right as a sort of, sociological and historical fact. It seems that nothing in physics depends on this sort of fact about mathematics. But I want to say somewhat more, which is that the thing that I'm sort of foregrounding is the role that the way we draw inferences about mathematical structures allows us to draw inferences about the world. And it's true that we use more than first-order logic in ordinary inference drawing in like ordinary mathematics, but it's also true that whatever sort of standard inferential practices that we have virtually never butt up against the kinds of considerations that are either themselves undecidable or depend on the kinds of things that would make that, the extra axioms or things. Like, we don't even need the axiom of choice for almost any of the inferences that we draw. And so, if we're sort of focusing on the inferential part, I think that, yeah.
Okay, I like this a lot, and I think I'm sympathetic. One of the things you said is we shouldn't be talking about symmetries of a theory. Right? And I regret to say sometimes I lapse into that. I want to know what am I doing when I'm doing that. So, for example, you might say, well, look, it's an important fact about Newtonian physics that as long as all the forces depend only on relative distances, you've got a Galilean invariant. The symmetries of the dynamics is a Galilean group, and so Galilean spacetime should be, the right spacetime. It's a fact about a classical electromagnetism that the Poincare group is the symmetries. What am I saying when I say things like that?
Okay, so all of that's perfectly
right.
Fine. You actually didn't have to say a symmetry of a theory in order to say the things that you just said. You said specific things about symmetries of dynamical systems, which I think perfectly sensible, and automorphisms of space-time structure, which are perfectly sensible, and drawing comparisons between those. That's the kind of thing that I think are fruitful applications of symmetry-based reasoning that allow us to draw these relationships, draw these inferences about structural dependencies. All of that is gold standard philosophy of physics.
Okay.
Do people know that this is an executive order from Trump recently that we're only going to do gold standard science from now on? So Wayne's doing it right here if anyone needs examples. The thing that I'm objecting to is maybe a little bit more parochial, but I detect it pretty often. I think that there are people who would like to take the kinds of lessons. I mean, so as I said, Gordon himself doesn't do anything that I think is all that problematic in his paper other than the title. Without naming names, I think that there are examples of philosophers of physics who would like to take the kinds of inferences that Gordon wants to draw there and elevate them to a more abstract principle of scientific reasoning, where if you present me with a theory, and it could be any theory, it could be just, the textbook version of a theory, it could be, your favorite toy theory, that there's some recipe for identifying the symmetries of the theory. Once I've identified them, I now know what to do. I need to get rid of them. I need to reduce the theory, come up with a new theory that doesn't have them. And then they illustrate with a bunch of examples. And I want to claim that none of the examples match the general form that they've presented. And in fact, you can't infer anything from the examples about a pattern of reasoning that's happening at the level of abstraction that people in the symmetries literature would like to endorse. So what you're giving me are, the kinds of things that people point to as examples, but I don't think that they should be thought of as, evincing the symmetries of a theory in anything like the sense that variational symmetries are symmetries of a Lagrangian.
Okay, wonderful.
Sorry. It always strikes me that when we reason about mathematics, we reason in, there's a kind of inductive process by which we think about mathematics that even if verification of mathematics is ultimately by some kind of analytic reasoning, and is that how? This is why I always think when people try and understand amplitude physical reasoning, I'm always like, well, even if that did explain it, would it explain mathematics? Well, some people are happy to try and explain away physical induction, inductive reasoning about physical systems, and I'm so. Is it important to understand how our mathematical inductive reasoning informs our physical inductive reasoning? I guess is my question. If this is a question, I'm not sure. Anyway, I apologize.
I'm not sure that I understand what inductive reasoning in mathematics means. I mean,
well,
you don't mean like, prove it for n equals 1 and then show that if it holds for n, it holds for n.
Well, no. I mean, how can we don't? The reason Goldbach's conjecture could be true or false. Any conjecture you could just randomly generate might be true or false, but Goldbach's conjecture is considered to be more interesting. We're more interested in whether it's true or false, and we don't. It would be kind of surprising if right now the news comes in that it's been falsified because a counterexample's been found. And we clearly didn't deductively arrive at Goldbach's conjecture is interesting. So by inductive, I just mean not deductive. And it can be exploratory reasoning. It can be, it's not merely verification, like some kind of, yes, false, true, judgment.
Yeah.
Necessarily, it's a whole bunch of other. There's a lot of reasoning that's hidden within the distinction. This is.
Okay, so I see where you're going, and I agree with you that there's something very rich about how mathematicians decide what to work on, what's important, what's interesting. Very often, I think, frankly, both mathematicians and physicists are guided by the same kind of thing, but it's like what kinds of things are most likely to lead to more interesting math or physics.
Yeah.
And so sometimes people talk about this in like like fruitfulness as like a guide to inquiry. So, I mean, I guess what I would say is there are really interesting questions about what mathematicians are doing when they're trying to identify things. I also think that physicists are very often motivated by things that are qualitatively similar, but I don't necessarily think that there's like an important mystery to resolve about why the things that mathematicians have found to be so interesting over the years have turned out to also be applicable in many cases to physics. It's mostly just a selection effect. And a feedback effect, right? The selection effect is many things in mathematics have not turned out to be interesting or important for physics. Mm-hmm. And many of the things that even mathematical physicists, I mean, are there any mathematical physicists in the room I'm going to offend right now? Okay. Here's an opinion that I have. Elliptic operators are useless for physics. I've said it. I'm sorry. Okay? Carlo doesn't think so. Oh, look. What's that? That's too much. Okay, it is a bit too much. Hyperbolic operators would be really great, but they don't have nice spectra, and so you can't do the kind of math that people like to do with hyperbolic operators, even though we have a Lorentzian geometry, and it would be really nice if we could give analyses of hyperbolic operators on a Hilbert space. And so there are disconnects between what sorts of things guide mathematical research and what kinds of things end up being applicable in physics. And it's, I think, a selection effect that leads us to think that somehow mathematicians are really great at anticipating what physicists are going to need. Is that better, Carlo?
So, Simon, I saw you too later.
Yes, so Well, provocative and beginning of a conversation. I thought really your talk is very interesting, and I find myself partly drawn and partly not drawn, and let me just try to explain why. So there's a way of thinking about symmetries, especially if we're interested in physics, where we look at a number of crucial moments in history which were tremendously important to physics, development in physics, that involved what certainly physicists call symmetries. Whether they're symmetries in the generalized sense that you have been talking about it, and this is a bit of the pushback that I want to give. I mean, if this notion of a symmetry is just, in mathematics, one's looking at maps, various kinds of structure-preserving maps, that is so remote from the ways that physics has engaged with, or rather, symmetries have arisen in physics. So, to give some examples, obviously Galileo's ship is the most famous. There's Faraday's cage. There's Einstein's elevator. I mean, but there's even just the fact that you do an experiment at different times, and it doesn't seem to make a difference to the experimental phenomenology and so forth. You translate the laboratory in space by 100 meters, doesn't change anything. You rotate it by 30 degrees, doesn't change anything. So this notion of symmetry in physics is tremendously important, and one would like to understand it from a philosophical perspective. As a philosopher of physics, I think we owe it to our training somehow to say something informative about this. And I don't know whether this, what I'm talking about, I'm not sure where it sits in your understanding of symmetries. And I worry that in a way you've so expanded the meaning of symmetry and extended it to mathematics quite generally, and no wonder you've lost sight of what is so important, or has been so important anyway, in the history of physics.
Okay, so I disagree that I've lost sight of what's so important. One of the many challenges of giving a talk that's trying to give a very big picture family of views is that invariably some things are going to get emphasized and others aren't. It's also going to be very disjointed, as this clearly was, right? You're supposed to assemble the pieces somehow. I'm not objecting to any of these instances from the history of physics as compelling examples of symmetry-based reasoning. In fact, I want to elevate them, but as particular instances of reasoning that involves, the fact that I can perform the same experiment at different times, for instance, is telling me that the laws of physics that I am probing in this experiment do not depend on time, right? Perhaps, for instance, I should think of time as a one-dimensional affine space instead of a real number line, because in fact, the number doesn't make any difference. What matters is difference in time, say, or duration. That is the kind of analysis of structural dependence that I think symmetries are extremely well suited to guide reasoning about. Those are the success cases. The thing that I'm reluctant about is trying to say that each of these instances of successful symmetry-based reasoning are best thought of as instances of a single pattern of reasoning, especially one that has the form, I take a theory, I identify the symmetries of that theory, and then I draw some inference directly from that following from standard pattern. What's going on is I'm showing that one way in which I'm showing that something does or doesn't depend on something else is by showing that I can transform one thing without transforming the other thing, and it won't make any difference.
Can I just make... I absolutely agree with you that it's not quite the right way to frame any of these examples in terms of here's a theory now, these are the transformations on it, they leave something invariant. That's because these are, as it were, pre-theoretical considerations, and actually they're operational. They're things experimental investigations that we can actually do. So So it's very different, and especially it's different from global symmetries, where you sort of transform entire contents of space-time or something like this, which is, of course, nothing that can be operationalized. So, but I think there must or ought to be, and if we can't find it, then we're failing, to say something that is fairly, what is this pattern? How is this so important and potent where it exists? We do need to address those cases. And one way in which we lose control of the subject matter is by addressing too much, as it were. So I just would wish to address a narrower.
Well, but I think we're agreeing about that, right? So I'm also saying that we should be addressing a narrower thing.
Okay.
The thing that I'm doing at the end is getting to the point where I'm going to give you my best attempt to say what something like general relativity is, and then give you a proof that diffeomorphisms are not symmetries of a theory in this particular sense. That doesn't mean that diffeomorphisms aren't extraordinarily useful for reasoning about structural dependencies in general relativity. The thing that I'm worrying about in what you're saying, so there are cases that look more operational. Many cases don't. The fact that some do and some don't, that's grist for my mill. The fact that some do look kind of pre-theoretic, as you say, I think is in tension with some of the things that I said in the talk. I seem to say that they're never going to be entirely pre-theoretic. I should think about that some more. Maybe I want to say something weaker.
Yeah.
I enjoyed a lot, Jim, this for the content and also for the style, and I suffered through also.
You suffered through it.
Yeah, but probably with a happy ending. First of all, you were giving a lot of things, so sometimes I would get lost, and while you were talking, I would say, no, come on, where is he going? At some point, I was saying, oh, come on, I mean, it's too much structure here, where's the world? But then the world came in very clearly, so I went. So I'm not sure I got the full picture, probably but I'm very sympathetic, and I want to come to specifically symmetry, and also to the kind of question that Simon was. For what I understand, I find myself very sympathetic with many things you say. I mean, in fact, some were very good to me, like your account of laws. I keep hearing there are two ways of thinking about laws. One is a Humanian mosaic. The other is the governing things going ahead. And I put my hand in my face. No, neither of them is good for me. I mean, this is not what law is much. And now you talk a law in a way which say, oh yeah, I could take law this way, and so on and so forth. I think I do understand what you're saying about symmetries, and it does resonate with something that as a physicist, has been bothering me over and over, that people confuses different kind of symmetries dramatically. And I'm talking about, often discussion with colleagues, that come from, quantum information and talk about quantum reference systems and say the symmetry, and they put on the same ground things which vaguely resemble to one another, but are truly, truly different. And the point you were making about Gordon, I think I was in his thesis committee, is possible.
Yeah.
Do you remember? Yeah. Okay. Yes. Yeah. I mean, there's. One of the specific confusions that come over and over and over again. In fact, in different. Often physicists themselves are confused, but I don't think good physicists are, is what is the distinction which was called gauge symmetries, where the known gauge symmetries, which is subtle, because when you do the standard model, for instance, the local SU3 symmetry is a gauge symmetry, but the global is not. So it has a profoundly different physical meaning, the two kind of symmetries. So when you say we shouldn't have a common account of symmetry, saying, oh, what is a symmetry here, and that's how you think about it. If we do that, we just put ourselves in a corner, and we're meant to say something wrong in some situation, seems to me. Okay, Francesca is saying go shorter. I guess what I want to get at is simply, there's no doubt that, in my opinion, there is even an overemphasis on symmetries. I have colleagues that say science is nothing about symmetry. Physics just about symmetry. Certainly they played a role. I mean, the standard model is another example for the particle physics, for saying the only thing we have to do is find out the right group and so on and so forth. I would interpret what you're saying, and that's coming closer to you, not only don't talk symmetry in a generic sense, but be very careful, and it will be useful, be a sort of taxonomy of different. In some sense, a lot of what you're saying, when you say group theory becomes crucial, group theory is just a way of talking about symmetry. Is a name. So symmetry is a lot of different things, which clearly plays a role precisely because we're looking at structures. So.
Yes.
Are we on the same ground, roughly?
Yes. Thank you.
Good.
Next time I'm invited to give a talk, I think I'll just bring you up and say, Carlo. I mean, look, this is exactly the sort of thing that's motivating me. And so what I'm observing are two tendencies, and I agree with you that physicists do it too, of sort of very quickly saying these are our symmetries, or this is gauge, when in fact these terms get used in very, very different ways. And there can be real errors of reasoning if you're not attentive to the differences. And again, I'm not saying that no one's attentive, and I'm not saying that we can't be clear about what's going on, but it can happen. And I think that there's a special tendency, because one of the things that philosophers of physics like to do, or philosophers generally like to do, is take some things that physicists are talking about and give an account of it. And so if you find a physicist talking about symmetry all the time, or saying that symmetry is, the logic of nature or something like that, you'd like to give an account of symmetry. And so then you end up with these literatures that are trying to do exactly that, without tracking that, in fact, we're using symmetry in different ways. And what I'm saying is the thing that's probably, I want to say is unifying the successful uses of symmetry in physics is rather that you're probing these kinds of structural relationships as they arise in different local contexts. And not that you're employing some, single method of symmetry or something like that.
So I would like to apologize to Mike and Chris because I'm gonna cut you, but I would like to give Miguel and Shelley the opportunity to give the last two questions. So Miguel first.
I apologize. There you go. Okay, my question isn't even well formed, so I feel like very bad about this. But I think it's important anyway. So. And it vaguely relates, I think, to what Simon said. I mean, it relates to you bringing up the idea of symmetries being, whether they're pre-theoretical symmetries, and it relates to sort of the normative implications of being some sort of inferentialist about structure. Mm-hmm. Because, I mean, what you say makes a lot of sense, if I understand it correctly, if we think about having a theory in place, and if we think about mathematical physics, I think. Now, one place where structure or structural reasoning has been very important is where we try to build new quantitative structures, especially in the human and social sciences, right? Mm-hmm. So like so much of the stuff that Supis et al. Are doing on structures is motivated by that, it's psychology and so on. So there the idea is like, we have some bits of mathematics, the additive reals, and we want to find something empirical that maps onto that. Right. So can we find some axioms that satisfy representation theorem on the additive reals? And so the normativity is the other way around, if that makes sense. I'm not quite clear. So I'm wondering if there's any implications of your sort of more inferentialist view on this idea, where we try to find some. I would say, like, I guess pre-theoretic. We try to use structure to constrain what we pre-theoretically have to find in the world, such that we can use a specific bunch of mathematics. I hope that makes sense.
Okay, so as some of you know, in my spare time, I've been writing a book about von Neumann for the last 8 years. Okay, so this is almost finished. But of course, von Neumann and Morgenstern introduced sort of the first representation theorem in this sort of the sense that you have in mind, right? And I think a lot of stuff, there are many different Suppies out there. I don't just mean like Fred Suppy in addition to Patrick or Frederick Suppy in addition to Pat Suppy. He did many things in his career. There was a point where he was doing the semantic view of theories as applied to physics, where he was coming up with these set theoretic predicates and trying to axiomatize theories in terms of that. That's the thing that I'm objecting to. The stuff that he's doing with like Tversky and the stuff he's doing with Duncan Luce, like that's a totally different thing. The representational theory of measurement, which I think of as downstream of like von Neumann Morgenstern style representation theorems, where what you're trying, right? Okay, so all of that's fine, and I do think that there are really interesting questions about what kind of structure like what mathematical structures you want to be able to, you're able to use to represent possible measurement outcomes for some kind of system, right? And there is a notion of symmetry that we can think about for the thing in the world, but also like very often what we're doing is we're saying we have pre-theoretic ideas about structure too, right? Like we kind of know that the number we assign to temperature doesn't matter. What matters is differences between temperatures. And although we always assign numbers, we already kind of know that they should be invariant because I can confer all the same information or convey all the same information with some uniform affine transformation on my temperature scale. And so I agree that there's a kind of symmetry reasoning that's going on there. But I'm not sure that it's a symmetry reasoning that's totally divorced from thinking about structure.
Yeah, no, I don't think it's, but I'll let Shelley, but I don't think it's divorced from it at all. But I'll let Shelley ask the question and I'll ask you
Okay.
about that.
Okay, cool.
Thank you so much. A lot of what you said reminds me of what Ryan Samaru called like Friedman's thesis. Oh, yes, sure, sorry. So a lot of what you said reminds me of this Friedman thesis, which, if I understood correctly, physical knowledge is stratified, and among the constitutive principles, we have mathematical principles. These are like delineate the mathematical possibilities, and he regards, for instance, Riemann geometry, theory of manifold, as mathematical principles, and these are prerequisites. And then there are also coordinate principles where we need to interpret mass and EM fields, and these establish an epistemic relation to the world. And I take a lot of what you said is kind of conveying the view that our physical knowledge is also stratified in some way. And in the beginning of the talk, I think there's a slide about the structure first approach to symmetry. So I'm curious also whether you take this kind of structure first approach to laws, or if maybe there's a hidden hierarchy behind the title. Do you take structure to come first as like a prerequisite to laws? I know we will probably not agree on laws in general, but I'm curious what you...
Like, because you're also a Humean?
I am, yeah. But I'm also curious if your account of laws is driven by this structure approach, if that makes sense.
Yeah, I mean, well, so certainly. So there are two parts to that question. One is, do I agree with Friedman on this sort of stratified view where you have these mathematical principles and these constitutive principles? And I think that the answer is no, but I'm not really prepared to say very much about Friedman on that. On the second question, I think the answer is yes, that I tend to think that sort of good empiricist or at least naturalist principles are compatible with a more robust conception of law as actually describing real modal relationships between how these sorts of things that we can measure would be under various circumstances. The basis for that argument is basically Miguel's talk, like the idea is that the success of a certain kind of counterfactual reasoning in the history of physics seems to involve taking laws seriously in a way that I don't understand how the Humean can make sense of. But one way of understanding what that involves is saying that, in fact, the world has this structure. And
The nature is kind. And
so kind as to give us this richly structured world that we can learn about through these methods.
Next way to.
Mm.